In this video, we are going to learn about a special type of one-dimensional kinematics called free fall. So at the end of this video, you should be able to choose the appropriate equation to calculate the acceleration of an object in free fall and describe the changing motion of the object as it falls from a written scenario. So free fall is a special type of kinematics problem that involves objects falling under the influence of the pull of gravity alone. Basically, that means that if I do a free body diagram of an object that's falling, the only force that is going to be acting on that object is going to be the weight force, or the gravitational force that's going to be pulling straight down towards the center of the Earth. So, for example, this guy who's jumping off a cliff, the only force on him is the gravitational force pulling him down. Now, all objects undergoing free fall are going to fall at the same rate. So if you drop any two objects at the same time from the same height, they are going to hit the ground at the same time. Now, we can say that, but pretty much everybody has experienced air resistance. So, for example, if you stick your hand outside the car window as the car moves, the faster the car is moving, the stronger you feel that push of the wind against your hand. So what causes that? That is something called air resistance, and air resistance comes from all of the atoms and molecules that make up the air piling up as an object moves through the atmosphere, and it creates a backward push. So, for example, we have our skydiver who's falling down, but all of these atoms and molecules, as he's falling, he has to be able to push them out of the way in order to break through. And as he's falling, he gets them bunching up underneath him, and they create an upward force that are going to slow him down. So the more the particles are compressed, the greater the opposing push. And eventually he will reach something called terminal velocity, where he'll actually stop accelerating and he'll start moving at a constant speed. But in the classroom, we can just ignore air resistance. So air resistance is absolutely very real, but in the classroom we can ignore it. And the reason for that comes down to a demonstration that obviously I can't do on this video, but I would like you to look at, there's a slide set right after the video that's called Try It Yourself. All you need is a book and a piece of paper that's about the same size as the book, and it'll walk you through the demonstration, so you should be able to see why we can ignore air resistance in the classroom. The short version of it is that we are using objects that break through the air easily enough that they aren't affected by air resistance enough to matter. Now, I'm also going to have two other videos that I'm linking below that are going to show you some demonstrations of objects that are being dropped without an atmosphere. The first one is going to be on the moon. Back in the early 70s, when they actually were landing on the moon, they did an experiment that was rooted in Galileo's experiments, supposedly from dropping objects from the Leaning Tower of Pisa, that he theorized that objects dropped at the same rate, and they did this experiment up on the moon. It's hard to see because this is 1970s technology, but you can see it. The second video is going to show you a bowling ball and a feather being dropped at the same time. And this one is going to be done here on Earth, but they are going to use a giant vacuum chamber. A vacuum is basically just an area of space where all of the particles of atmosphere have been removed. So all of those atoms and molecules that build up to create air resistance are removed, and so we can have everything drop without that air resistance. So those two videos will be linked just below this and just below the Try It Yourself activity. The other two pictures here, this one shows a bullet that is trying to break through that atmosphere, so everything's piling up and it's creating a barrier, and the bullet is breaking through that. That's causing the bullet to slow down. The one with the space shuttle, that is the friction of the space shuttle moving so fast that the rubbing against all of those particles of atmosphere basically create intense amounts of heat. And so the space shuttles have to have special shielding in order to be able to break through the atmosphere without burning up. All right, so these are some facts that you need to know about free fall. and when we drop an object. First, in free fall, the acceleration near the Earth's surface is a constant. And instead of a for that acceleration, we use g, which stands for the acceleration due to gravity. And that constant here at the surface of the Earth is 9.8 meters per second squared. The acceleration due to gravity is always down towards the center of the Earth. And when we do free fall problems, in this class, the initial velocity will always be 0. We are always going to drop something starting from rest. And the only factor that affects the time it takes an object to fall is the object's initial height. Now, we also can have free fall when we throw an object up into the air. As soon as we release it from our hand, the only force acting on it is going to be the gravitational force again. And so the object is in free fall, even though it is moving upward. Now, when we throw an object upward, at the top of the object's path, the velocity is going to be 0. But the acceleration is always 9.8 meters per second squared. It doesn't matter where the object is. Here, acceleration 9.8. Here, acceleration 9.8. Here, the acceleration is 9.8. Here, the acceleration is 9.8. At every location, the acceleration will be 9.8, even when the object is at rest. And at the same level, the object's speed will be the same, but the direction is going to be opposite. So if he releases the ball at 10 meters per second at this height, when it's on its way back down at the same height, it's going to be moving at 10 meters per second, but in the negative direction. If this is 7 meters per second up, this is 7 meters per second down. And any object thrown with the same upward speed will reach the same height and stay in the air for the same amount of time. Mass does not matter. So this just shows basically the same thing, gives it some numbers. So if we look at the distance between each of these is 1 second, our object is slowing down as it moves up and speeding up as it moves down. And that change in speed is going to be the same for each time interval. So how do we solve problems with free fall? Here's our first example. An apple falls from the top of the tree. If the apple takes 1.2 seconds to hit the ground, we want to know how tall is the tree. Well, our time then is 1.2 seconds. We're looking for our height, or our how tall. But we don't have any other information directly from the question. So in free fall, we do have two assumptions that we can make. First, acceleration is 9.8 no matter what. And the initial velocity is going to be 0. The apple is going to be dropping from rest. So from that, we can go ahead and choose our equation. So is acceleration in the problem? Yes, it is. We are looking for distance or height. We know time. We know initial velocity. So the final velocity is the one thing we don't know. So this is the equation that we're going to use. But what we're going to do with free fall is we are going to change this into a slightly different version. So the original equation, delta D is equal to initial velocity times time plus 1/2 acceleration times time squared, is going to change a bit. Now our initial velocity is always going to be 0, which means this entire term will always be 0. And instead of D, I'm going to use H for height because we're generally using a height. So our equation is going to be 1/2. Our acceleration is always going to be G and T squared. So this is the equation that we're going to use to try and find how high something is falling from. So in this case, we have height is equal to 1/2, 9.8 meters per second squared, times our time of 1.2 seconds, and we're going to square that. Now we're going to do this in the calculator. It's easiest to take the 1/2 and make it a 0.5 times 9.8 times 1.2 squared, and that is a height of 7.1 meters. So that would be the height of the apple before it fell. So let's try another example. The apple falls from the top of the tree. The apple takes 1.2 seconds to hit the ground. We did the how tall is the tree. We want to know what is the velocity of the apple just before it strikes the ground. Well, we knew there are 9.8. We now know that this is 7.1 meters, 1.2 seconds, and let's see, our initial velocity was 0. So to find our final velocity, we can actually use any equation that has final velocity in it, but we generally want to use the simplest one, which will be this one. So if we have our A is equal to final velocity minus initial velocity divided by time, I need to solve it for final velocity. And what that's going to look like is this. But, of course, our initial velocity is always going to be 0, so our final velocity is just going to equal gravity times time. So in this case, it's going to be our 9.8 times our 1.2 seconds, and that is 11.76 meters per second. So that's how fast the apple is going to be moving just as it strikes the ground. All right, so in your notes, I've given you these 3 equations as some alternates that we're going to use. This one here, our simplified version of that is height is equal to 1/2 gt squared. And on any tests, you will get these equations in case you need them. So let's do our one last example, and this one's going to be for time. The apple's falling from the top of the tree. We want to know how long, or time, does it take the apple to fall the first 1.5 meters. So our equation is time is equal to the square root of 2 times the height divided by the acceleration due to gravity. So that's going to be the square root of 2 times our 1.5 meters divided by our 9.8 meters per second squared. And when you do this, do all of the math in steps. So 2 times 1.5 is going to be 3. So 3 divided by 9.8. 3 divided by 9.8 is 0.306. So now let's take the square root of that, and our time is going to be 0.55 seconds. All right, go ahead and do the try it yourself activity, and then go ahead and watch the other 2 linked videos, and then you can work on the problem.